My name is Chris Thorsen. I'm an associate professor here at the School of Computer Science. And I wanted to tell you about some of the progress that my team and myself have made on the issue of artificial general intelligence in the past 5, 6, 7 years. So I have worked with a number of people over the past few years, and here I list some of them. You'll, of course, be able to look at my collaborators' publication list if you Google any of these names. And we've already talked a little bit about what does AI mean, and now there's a new G in there that I would like to talk about very briefly before I show you some of the results. So you may be familiar with Google's attempts at creating self-driving cars. And frankly, if you've been paying attention, you will probably know my opinion of where this fits in the spectrum from specific to general. Obviously, this is more or less a one-trick pony, or one-trick Prius. And a fundamental thing here, which actually runs through all of the talks, is that we want our systems to learn. So then the question comes up, and it sounds pretty simple question, how do we create a machine that learns? Well, there are many ways to learn, turns out. And one of the hardest ones, but one of the most powerful ones, is learning by observation. And you know that people, if you're a person and not a robot, you know how you came to acquire the information that you have in your head. And you know that imitation is one of the strongest ways that students learn. And we probably have plenty of examples of this in nature, although I'm not going to argue that here. But even the most advanced skills are acquired in part by observation. Now, it turns out that we really don't have any systems that can really learn properly by observation. Not at least in the same sense as we are familiar with from human learning. So we asked ourselves, could we create a system that would be able to learn a fairly complex task that no system yet to date has been demonstrated capable of learning, purely by observation? What we picked was basically the task of a TV-style interview. The observation material that our system should be looking at is not trained actors, but actually average human beings like you and I, who are talking about a particular topic, and I'll get to that in a minute. With naturally occurring deictics like this phone. Why? How do you know I'm not talking about this phone? And so on. At least 100 words, and a pretty much non-scripted scenario. So we moved this interaction. We knew fairly early on that we were not going to use computer vision. So we moved this interaction between these two humans into cyberspace. Essentially, it's like a video conference, except you don't see the other's video feed, you see the other's avatar. But otherwise, this situation is exactly like a Skype call. You are talking to each other. In this case, there's a table between you, and there are objects on the table. The aim here is to demonstrate that it is possible for a machine to learn very complex temporal skill that has to do with timings of events on many levels with very little information up front. So this is unlike GDP in that there is no way for us to write down all the rules a priori. It's a naturally occurring interaction between two humans, so there's a lot of variation. You can't really control it scientifically. And if we want someone to learn interview style from observation, from observing two people interacting like that, it's not enough to imitate movements. It's not enough to imitate surface phenomena. The system has to figure out the reason for why the people are doing what they're doing. Otherwise, it will be more or less like a video recording, maybe cleverly indexed. So what we're after here is a system that can acquire some rules about the task that it's observing, and do so autonomously with very little knowledge up front. And what we really are talking about here is we are trying to move towards true machine understanding. And to achieve this, we had to do a number of things. It was quite a bit of work. In fact, addressing the whole stack all the way down to the operating system. We did not write a new operating system, but we did implement and invent a new programming language, a new kind of reasoning that was implemented, a new kind of programming paradigm for this new programming language and logic. And on top of this, we implemented an architecture that runs the system, looks at the data, streaming in real time, and tries to figure out what's in it. Basically, what we're talking about here is a new methodology for creating AI systems. The scenario, the setup for testing our system essentially is like this. We've got this video conferencing situation where the actions of person B are shown immediately on person A's screen, and vice versa, speech and gesture. We're tracking the movements with special apparatus, and we're basically recording the speech with microphones. The S1 agent, which is our first agent in this architecture, is watching the data stream. I'm not going to go into details about what exactly we put into the agent. Feel free to ask me afterwards, and I can tell you all about it. But and there are papers out there as well. It's too technical for now, but let me just give you some examples of the kinds of sentences. And remember now, the agent has very little knowledge a priori. It is not given any syntax whatsoever. It doesn't even know what words are. Here are some examples of utterances that S1 has to observe and figure out why they are like they are, when they are produced, what rules, in fact, govern the sequence of these tokens, which the words actually are in the data stream, and so on. As you can tell here, the interaction is about recycling. So there are 6 objects on the table in front of the people. Plastic bottle, glass bottle, newspaper, and so on. And the answers here are all true. They're true statements about recycling and the comparison between the cost and pollution involved with recycling some of these materials. So S1 observes an interaction between humans for 20 hours. We set ourselves basically the task or the goal of having the system observe this interaction until the performance was pretty good. It's a rough outline. And then once it's observed this interaction, seen plenty of examples of questions and answers and sequences of QA and manipulation of objects and so on, it actually replaces one of the people in the stream and controls the avatar on one person's screen directly. So now let me show you some videos. So just a brief example of the behavior of these two humans. This is what S1 sees as the humans interact.
Tell us about this object.
This is an aluminum can. The main ingredient in aluminum is bauxite.
What else?
All metals are recyclable. Aluminum can be recycled virtually endlessly. A recycled aluminum can costs 95% less than a new one.
Which takes more energy to make, an aluminum can or a plastic bottle?
It takes more energy to produce a can of aluminum.
Okay, so this is not a lecture in recycling, but you get the picture. Now, after 20 hours of observing real interaction, non-scripted, this is what we see S1 doing as an interviewer.
About this object.
This is a glass bottle. Glass can be recycled by grinding into filler. Most glass can be recycled endlessly as long as it has been sorted properly.
What else can you tell about it?
Glass bottles can be washed and refilled.
So you see here, the machine is on the right-hand side.
What is this thing?
This is a cardboard box.
And let's quickly go to the last one, which is the machine interviewed by the human, which is my favorite.
What is this object?
This cardboard box is made from natural wood fibers. Wood comes from the forest or from recycled fiber. Fiber cannot be recycled endlessly like metal. Cardboard boxes are biodegradable. Cardboard box take 2 months to disintegrate in the sun.
What is this?
This newspaper is made from natural wood fibers. Recycled paper can be used to make new paper.
So nothing about this behavior of S1 here was scripted or given a priori. Essentially, all of the grammar rules, if you could call it that, are acquired by the system autonomously. The system did not know anything about an interview, except that the goal of an interviewer is to get the interviewee to talk. And the goal of the interviewee is to please the interviewer. So very high level goals, and then plenty of observation time. So that is essentially the scenario and results we got. Now, what is this really? What is learned here? Well, the interleaving of questions and answers. As an interviewee, what and when to answer when asked a particular question, the timing of that, the timing of the word output, how to formulate an answer, how to refer to objects with a deictic gesture or manipulation of this sort. And as an interviewer, what to ask, when to ask, how to formulate a question, how to use a particular technique to keep the interview within time limits, and how to sequentialize questions in an interview. Multimodal coordination, take turns when speaking. A silence from the interviewer probably means go on. A nod means continue, and so on. And language, what to answer, what to put into an answer when asked a particular question with a particular set of words or a deictic gesture. Tell me about this. And maybe the most astonishing fact here, to me at least this was a surprise, S1 makes no mistakes. There's no way to tell that this is a machine actually doing the interview except for the voice. So we have a new kind of learning here. It's a goal-level imitation learning. And we're very excited about it. Some features of this, which we won't go into details on, essentially these are model-based, autocatalytic, and attention-driven, time-sensitive knowledge acquisition based on observation. And we have here an example of bounded autonomy. We're very excited about what can happen in the next few years with this technology. We have a small team, so we are working very hard to explore some of the most exciting possibilities. So that's it for me. Thank you.
Injecting the robots into the conversations, did you tell the other person that that was the machine at that point?
When we did the experiment, did the other person know that there was now a machine on the other end? Yes. First of all, of course, they heard it, but due to the experimental setup, this was an unavoidable side effect of just the methods we used. Yeah. But that would be an interesting way to explore sort of the illusion here. Yeah?
Did you translate the voices into text before you learned them?
Yes. There is we used the best speech-to-text recognizer we could find at the time, and we time-stamped the word. This was something that Eric Nivell, my close collaborator, had to do because most speech recognizers actually don't timestamp the words, but because S1, our system is very has a very keen sense of time, and this is like an essential property of the system, and quite a novelty actually. We had to ensure that the system knew at what time things happened, otherwise it could not learn properly. So yes, the words are essentially piped through a speech recognizer, and we try to timestamp them with a timestamp that indicates when it was uttered. Otherwise, the system, but the system knows nothing about words per se. It's just a type of data. Yeah.
So when S1 learns how to manipulate an object that is like, tell me about this thing, and like they pick it up, then is that a single action? Like how is this represented? Or is it a multiple, like I'm moving my hand here, then I'm closing the hand?
Good question. So what does the system know, or how does it differentiate actions in the 3 space? The objects are, so the whole geometry is inspectable by the AI. So the AI actually sees everything that happens as labeled objects, 3D geometric objects, graphical objects, labeled with a few tags like hand, arm, and color, something like that. So the plastic bottle has the tag in its data structure somewhere, bottle, okay? And it has a color colon and then the color code. But there's no knowledge in the system that blue refers to something called color. It has to figure this out. It has to figure out that something in the data stream coming from the speech recognizer actually may map to some tags on objects. In fact, it could be that these tags were actually on the head, on the avatar's head, etc. But this is how we actually link also the goals to the avatars, because we tell the system a priori what the top-level goals of the interviewer and interviewee role are. And the whole object, the avatar object, is labeled avatar. So that's how we refer to it in the goal structure, in the seed that we give, the knowledge seed that we give the system. And so for manipulation, there's nothing that says, when I move something or when the XYZ of an object change due to an action of the other avatar, like this, there's nothing in the system that says a priori that is something that I should map to the stream of things uttered. It has to figure that out. And it also has to figure out the timing of when you do this and that you don't use, tell me about this thing, and that is exchangeable with tell me about this plastic bottle. And in fact, that there's this redundant, tell me about this plastic bottle. Because there's only one plastic bottle there. So anyway, I hope that answers your question. Yeah?
What if you try to cheat the system? I mean, because you're providing that idiosyncrasy. What if you put label border when you should say box? Does the system then realize that there is something funny going on?
The system knows, I'm not sure I understand your question. Maybe you could paraphrase.
I mean, you put labels to those objects, and the system could see those labels. So
Correct.
What if you put the labels in the wrong places?
So if the labels are in the wrong places, and that's a good question. And the people are actually using the same words to refer to objects, it would not matter, actually. It would figure out that correspondence.
So you cannot cheat the system just by changing the labels?
Yeah, because the system bootstraps itself by observing correlations and co-occurrences of things. And it's very bad in the beginning, but it quickly ramps up. As it gets a good foundation, it can quickly layer on top. So that's in fact why my PhD student actually is focusing on how to guide such a system. So it goes back to Klaas's comment about the teaching environment, because we're now talking about systems that learn by experience. So we have to think about how the teaching and learning environments are designed. If you start with the hardest math and then go backwards, you're not going to get very far. Okay, I think we're out of time. Thank you very much.